Can you hear me now? Is anyone able to hear me now? Okay. Thank you for reporting the problem to me. Okay. So I said that last week we talked about we continued on the topic of state space representation for discrete time systems. So we did this example of the mass spring damper system. We found from the from the diagram of it, we're able to get the dynamic equations for the mass spring damper system. Then we represented, which is this. So we represented the system as a transfer function, after which we also represented the system as a transfer function in the continuous time domain. Then we represented the system as a transfer function in the discrete time domain, that's in the Z domain. Then after which we proceeded to find the state space representation of the system in the continuous time domain and in the Z domain. So I told you that for this class of today, we are going to, because in the last class we did not consider we didn't include the zero order odd into the transfer function. And the zero order odd is used by the computer to convert from the discrete time into the continuous time. And we, because the computer has analog and digital converter and digital to analog converter, so the computer doesn't see things in the discrete, in the continuous time domain. So the S domain is the continuous time domain. And that's not the way the computer sees it, because the computer is a digital computer, is a discrete system. So it sees the system as if it was in discrete time, so in discrete time unit. And it uses a zero order odd. The computer uses a zero order odd to actually convert from the discrete time domain into the into the continuous time domain, which is what is available in the real world. So we need to be able to represent the system exactly the way the computer says it. So this was the transfer function we developed last week. And now we want to include the zero order odd. Then we'll derive the transfer function for the system in the Z domain, which is like the proper representation. After which we'll go to the state space representation also in the Z domain. So this is a transfer function in the S domain. Now, including the zero order odd. So the transfer function of the zero order odd is given by is given by yes, I'm recording the class, so you'll be able to get it after the class is over. So the transfer function for the zero order odd is given by, this is the transfer function for the zero order odd. So, but in the last class, we just used this particular transfer function and we just converted directly into the Z domain, which is not appropriate, because in the computer you have ADC and DAC converters. So as a result of the influence of these converters, this is not really the transfer function the computer is saying. It's another transfer function due to the influence of the zero order odd. And I said that the zero order odd is the DAC, that's the digital to analog converter, is the model of the zero order odd. So in equation from this is the DAC. So we are including the DAC into the transfer function to be able to really see things properly the way the computer is seeing it. And this is the transfer function we got. So you simply apply this transformation to the transfer function and you arrive at this particular, you just multiply this and this together and you arrive at this. And the next step is to convert it into the Z domain. So the transfer function we get after converting to the Z domain is actually the view transfer function, not the one we got the last week. So this, the Z transform, so the Z transform of this, let me just put it in a, okay, the Z transform of this is equal to this is given by this expression here. So, and the way we do it is that, so we have this now. So we want to get the Z transform, but including the effect of the zero order odd. Then we are going to break this this particular equation down into two. So for this particular expression here, is the same thing as this. Then multiplied by this expression here. So this is just separating, it's just breaking down this equation into two. So the Z transform of this expression is given by 1 minus 0 raised to power minus 1, because here you have 1 here is 1, then the Z transform of exponential minus st is z minus 1. So you have, we've already gotten the Z transform of this, which is this. Then we want to get the Z transform of this, which is simply G of S. Remember, this is our G of S here in front, which is simply this G of S divided by S with the inclusion of this S. So since we've got the Z transform of the first part of this one, it's just remaining for us to get the Z transform of this. Then after that, we just multiply the result of this expression with this we have here. So further simplification of this expression, this highlighted expression, we give you this one. Then we want the Z transform of this. Then remember these steps, there are actually 3 methods we actually use to convert from the S domain to the Z domain. So the first method is to break down this, the expression into partial fraction. After breaking it down, you convert to the time domain. Then after that, you convert to the Z domain using tables. So here is breaking this transfer function down, this fraction down into partial fractions. So I actually skipped the step. So you have S here, then you have this second order polynomial. So is A, when you break down this one into the two factors, so you have this and this. So the when you break it down, you're going to get this expression. So I actually skipped that step. Then after that, you convert into the time domain, after which you converted into the z domain, after which you will convert into the z domain. Then to convert this into the time domain, I also skipped the step. So the conversion of this into the time domain is 0.0307 exponential minus 7.2361t. So same with this, then same with this. So when you convert back into the z domain using the tables, so you already have the z tables, you are going to get this expression. So converting this, so this is like a step signal, and the z transform if a step signal is z divided by z minus 1. So you simply have this. Then the z transform of an expression of this form is given by this. And the z transform of an expression of this form is given by this. Then after that, we have to expand it, then you collect like things. And this is the denominator. So you would bring the denominator together and you will get this expression. Then you convert this tree into a single fraction by, for this particular one is, and note that z is common to every one of them. So here you have z, and here you have z. Yeah. So when you just so when you account for this, it's z minus exponential minus 2.764. So this multiplied by this, then you multiply it with this coefficient. So for this second fraction, it's just this multiplied by this coefficient here. Then for the last one is this highlighted equation multiplied by 0.05. Then after that is actually a long calculation. So yeah, I simply brought out the numerator here. So I brought it down here and you arrive at this expression. Then after that, you would expand. So when I multiply this, I got this. When I multiply this together, I got this. And when I multiply these two together, I got this. Then when you expand this out, so including the multiplying it out with the coefficients, you arrive at this expression here. Then t is the sampling time, because this equation is actually very complex. So to simplify things, I included the sampling time, which is 0.01 seconds into the calculation. So when you put in your account for this t here and you put it into this highlighted expression, you are going to arrive at a simplified form. So actually, this highlighted expression becomes equal to becomes equal to this. So this very complex expression reduces to this. So you know you have z squared. So the way you reduce it is that you bring out the z squared, you add the z squared terms here. So this is z squared term, and this is also a z squared term, and this is also a z squared term. So when you add all the z squared together, it's actually 0. So when you add this plus minus this, then plus this is going to give you 0. So so when we did this, we just got, this was what we got. So which shows that there's no z squared term. So there's no z squared term. Also, the z terms, you will just add all the z terms together. And when you add all the z terms together, you arrive at this times 10 raised to the power minus 5. Then the terms that don't have a coefficient, so this and this, all the terms that don't have a coefficient, and this, when you add it together, you arrive at this times 10 raised to the power minus 5. So the numerator reduces to this, while your denominator is this. And remember that what we just simply did was the z transform, of this. So now we have to multiply it by z minus 1 divided by z. So when we multiply what we got here by z minus 1 divided by z, the z minus 1 will cancel out. This z minus 1 is going to cancel out here. Then z is going to cancel out here. Then you arrive at this. So this is the expression for the transfer function using the zero order odd. Then simply you just expand out this. We got this. Then you include the t. T is 0.01. When you include the t, you arrive at this polynomial. Then the z transform of this mass spring damper system, including the zero order odd, is given by this expression. So what we did last week, we didn't include the zero order odd, and this was the transfer function we arrived at, if you can remember last week. And you can see that they are very different. And this is the way the computer actually sees the transfer function, because the computer is made up of ADCs and DAC, because it processes signals in discrete time. Meanwhile, the outside world is in continuous time. So as a result of the converter, DAC converter, the computer uses, this is actually the transfer function, but this is supposed to be the transfer function. This is the ideal case. But because of you are in discrete time system and you are making use of the DAC, so this is actually the way the computer sees the transfer function of the system, not this, because this is the ideal case, but it's not, that's not the way the computer is seeing it. So we've converted the mass spring damper system into Z transform using, including the zero order odd. Now we want to convert, so this particular transfer function is the same thing as this. So here there is 10 minus 5, but when you include the 10 minus 5, it's actually the same thing as this. So this is the transfer function here, and it's the same thing as this. So what I simply did in order to get this transfer function is to simply bring out this one here, because now we want to convert into state space. So that's why I'm doing all of this. So I brought out this, then I equation 2, then the remaining part is this is the denominator here. So since I brought out this, So this numerator divided by this is going to give you z. Then this particular expression is just uh, this particular expression is just divided by this. So if you do the math, you discover that this expression is the same thing as this expression here. All I simply did was to bring out this 10a. So I divide both sides of the numerator by this. So that's why you have it this way. So you can just confirm for yourself that this is it, because when you multiply this by this, you're going to arrive at this expression here. And this calculation is 0.9645. So that's why I got this. So we'll follow the steps. I want to convert it into state space. So we follow the steps we normally follow. The first step is to divide by the highest power of z. So you divide both sides by z squared, and you arrive at this expression. The second step is to split the transfer function into two. And we split it into two by, so this is one equation. Then the other equation is given by this. Then the first expression is given by this equation, while the second expression is given by the remaining equation. Then you cross multiply to make y of z the subject of formula in the first equation, and to make a of z the subject of formula in the second equation. So this is y of z in the first equation, then this is a of z in the second equation. After that, so we arrive at these two equations. After that, the state will be defined to you. So we define z minus 1 a of z as x2 and z minus 2 a of z as x1. So in place of z minus 1 a of z, we are going to put x2. Then in place of z minus 2 a of z, we are going to put x1 in the first and in the second equations. So when we do that, we arrive at these equations here. But we need to get the relationship between x1 and x2. So the relationship between x1 and x2 is given by this. Just using these two equations, use it to find the relationship between x1 and x2 to get the third equation. So you have the three equations now. Then we want to convert into state space. First of all, you have to convert back into the time domain. Then I already told you how to convert from the z domain into the time domain. This is the z domain representation, and this is the time domain representation. So you already know how to do that. Then the state space representation is x k plus 1t equal to ax plus b u of kt. Then y of kt is equal to c x of kt. So that's the state space representation in the discrete time. So using these three equations, we'll just construct our A matrix, our B matrix, then our C matrix. But remember that it is in this form. X k plus 1t is equal to A x of kt plus b u of kt. Then y is equal to y of kt is equal to c x of kt. So this is what we got using with the zero order word. Then if you can remember last week, this was the state space representation we got in without the zero order word. So you can see that it's very different. We have different transfer functions. So in this case, I just switch the states. because for here, I said that let S2 be Z minus 1 E of Z, then X1 be Z minus 2 E of Z. So when I switched the states, I said that let X1 be Z minus 1 E of Z and X2 be Z minus 2 E of Z. And following the same steps, you are going to arrive at the different, going to arrive at different transfer state space representation. So this is like how to convert from a transfer function in the time domain to a transfer function in the z domain using from the first principles, that's from the equation, how to actually convert it. So this will be the end of the class for today. So next week, by this time next week, I would give you a short quiz. So by this time next week, you'll be actually writing a quiz, and the quiz is going to be based on state space representation of discrete time systems. So you're going to be a very short quiz, less than 5 minutes, and based on all the topic we've done, that's state space representation in discrete time systems. I'll give you a short quiz based on that. So start preparing for based on what you've done. Just this topic only, not everything we've done in the course, because you'll be writing a quiz by this time next week. So the next topic after this is we are going to use MATLAB, because as you can see, these calculations are really complex calculations. So, and it's prone to mistakes and everything. So after this class, the next class is we're going to use MATLAB to be able to solve all this. That's giving a transfer function, like this particular transfer function, how to convert it into the Z domain. So this is G of S, how to convert it to G of Z using MATLAB. Then how to convert it in state space from the transfer function, how to convert it into state space in MATLAB. So that is going to be the next topic. So this is the end of the class. So start preparing for it's going to be very simple quiz. Just based, like I said, just based on this topic only.